Hello, I am Ramon Lapina, and I'm here to talk about my project, which is an ASK modulator. So, an ASK modulator is a device which modulates a binary signal into an amplitude shifting one. Usually, the output signal of this type of modulation would be a sine wave, a fast shifting square wave, or a short spin wave that would eventually signify whether the signal projected is at its binary 1 or 0 corresponding to the input. So in layman's term, this type of modulation would project two signals of different amplitudes in which one of them would represent the binary 1 of the signal and the other with the binary 0, as you can see on the projected waves below. For this project, I was asked to create an ASK prototype that inputs a binary square wave and an output modulator wave with a frequency of at least 20 kHz. The circuit should indicate the change in amplitude when the binary input wave is in high or low volumes. So, the important components used in my circuit are, first, the 5x5 timers. I used two 5x5 timers such that one is used for generating the binary input and the other is used to modulate and generate the ASK output. Reactive components. Reactive components such as capacitors and inductors were used in order to generate a sinusoidal-like wave. The LC circuit was assumed to operate near its resonant frequency in order to make the output frequency stable, and the transient of its components would be fast, such that the waveform would resemble a sinusoidal wave. And lastly, the flipper circuit was also used for the modulator in order to minimize the spiking of the output waveform generated by the modulator. It sets a specific voltage wherein it does not accept voltages that were above the required voltage configured to the flipper circuit. Now, let us look at the schematic diagram I designed using the multi-seal. Okay, so as you can see here, one 5x5 timer circuit resembles an astable 5x5 timer operation. Its corresponding output would be a square wave that is inputted at a given period, which is being set by the resistors and the capacitor at its right. Okay, so notice the output of the left timer circuit at pin 3, as it is being connected to the control voltage which is at pin 4 of the other 5x5 timer circuit. This is in order to vary the comparator voltages within the IC, such that when the binary input is at high, the other timer circuit, this one, outputs a constant short spin voltage, and when it is at its low, it doesn't output anything but it applied 0 volts. So at its output, capacitors and inductors are connected just here in order to operate the output near its resonant frequency, to make the output frequency stable, and the transient of its components would be fast, such that the waveform would resemble a sinusoidal wave. And here, the flipper circuit minimizes the spiking of the output waveform generated by the modulator, in which I can show you later on. It sets a specific voltage required, wherein it does not accept voltages that were above the required voltage configured to the flipper circuit. Now, let us look at the simulation using the oscilloscope. Okay, so waveform 1, which is yellow, projects the general output wave of the ASK modulator, which is at the flipper circuit. Waveform 2, which is blue, projects the binary input wave of the left 5x5 timer. Waveform 3, which is the purple one, it indicates the output waveform before it is passed through the reactive components, which is located here. And then waveform 4, which is green, it projects the waveform of the RLC circuit, which is here. Let us move this further. Here. There. Okay. As you can see, at pin 3, from the other 5x5 circuit, it projects a waveform which is like sharp spin, just like in waveform 3. Here, waveform 3. As it passes through the RLC circuit, it's here. It's so hard to zoom, but okay. As it passes through the RLC circuit, it becomes like a sinusoidal waveform, just like in waveform 4. However, it spikes up and gets back to normal when the binary input switches from low to high, as you can see here. Oops. There. Okay. So, in order to solve this problem, or in order to address this problem, I added a clipper circuit. So the clipper circuit clips this spike, and then it results to a much cleaner waveform, which is the waveform 1. It's here. Yay. Though, as you can see here, the output wave is kind of like distorted. There, it's not like really much of a sine wave. It still reaches the appropriate specs, such that it operates at a frequency of more than 370 kilohertz, or specifically it's like 383 kilohertz, and it emphasizes the shifting of the highs and lows of the binary input. Here. It fits in, right? Yeah. So okay, after this, let's look at the design, PCB design. Okay, so in this PCB design, you can see the red paths and green paths across the layout of PCB. So the red paths represent the bottom part of the PCB, and the green paths represent the upper part of the PCB. For the actual PCB, only the bottom part is used, since the upper part is only used for indication of jumpers to avoid confusions and errors. You can see it here clearly in its 3D. Here. So this part here, this is the only part we will print. The top layer will just guide me as to where the components will be placed, where the pins of the IC should be located, or what portions of the PCB is needed to be used with a jumper wire. And also, simulated the circuit using a breadboard. As a evidence, let us look at this clip. Here, only the input and output waveforms are projected, just like in multi-SID. However, the waveform 1, which is the yellow one, it represents the binary input, and the waveform 2, which is the blue one, represents the output waveform, the ESK modulator. So once again, I am Ramon Pina. This is my project, and thank you for listening. Stay safe.